Assalamualaikum. So we'll start with chapter 3, induction machine for ELE291. So at the end of this chapter, you should be able to understand the principle, operation and construction of induction motor, and then solve the equivalent circuit. So you'll be introduced with equivalent circuit, and then the term slip, and also related terms such as speed, torque. Okay, in this for your syllabus, we use the approximate equivalent circuit, not the actual equivalent circuit. And then you should be able to understand and determine the power flow diagram. Okay, that is new as well. Losses, and at the end calculate the efficiency. So on the theoretical part, I will go through a bit quick. I mean not from word to word. Okay, so introduction. So induction machine is an AC electrical machine. So the supply is AC voltage. So induction machine uses AC supply to operate. So in terms of the construction, it consists of rotor, that is the rotating part in the middle, as well as the stator, that is the static part. The static part. Okay. So stator is the static part, and on the stator, as you can see here, there are windings. Okay, windings. So AC current is directly supplied to the winding on the stator here. Okay, and then as the result, um, a rotating magnetic field will be produced around this winding. Okay, rotating magnetic field. Okay, for rotor, it's a rotating part, so it is placed in the stator in the middle. So it is separated by a gap between the stator and the rotor. Okay, it's the rotating part. Okay, on the rotor, there is also winding on the rotor. So current were induced. Okay, just now current for stator is supplied, but for rotor, the current were induced. Okay, for the rotor. Hence, that is where the word induction machine comes from. The current is induced. Okay, so the other name for induction machine is asynchronous. Why is due? It is actually due to the difference in rotor speed and synchronous speed. In other words, for induction machine, we have two speed: speed of the rotor as well as speed of the rotating magnetic field, or we call it as synchronous speed. Okay, because these two, NR and NS, is not the same, so that's why it is called asynchronous, not synchronized. Okay. Induction machine can be used as generator or motor. So any type of machine can be operating as generator or motor. However, induction generator is not preferred because induction machine generates active power and consume reactive power Q rather than generating both P and Q. On the other hand, motor is more widely used for induction machine. I mean, induction machine is widely used as motor instead of generator. So in terms of application, for small and medium induction machine, and these are examples of application. It is used for the motor in the fan, washing machine, blender, refrigerator, most of the time for household application. But for large power induction machine, usually for industrial application, okay, for cranes to lift heavy loads, hoist as well, centrifugal pump to pump any fluid, and then also for the compressor. Uh, just now is the two main part of any induction motor, but induction motor can be found in two types or two main construction. either squirrel cage induction machine or slip ring induction machine. That depends on how the induction motor is built. For example, the first one, squirrel cage. As you can see, the rotor bars looks like squirrel cage. Okay, so this is the more common structure, whereby the windings are wounded on a stack of laminated steel slots. Okay, and then rotor consists of bars, okay, that were laminated by copper, and then rotor bars were mounted at the end, rings with bolt and screws. So the description is the description can be seen from the figure here. You can compare it with the second type, that is slip ring. Okay, very different. For slip ring, the rotor consists of three-phase winding that were wound in the rotor slots. So on the rotor, it has external resistance placed outside of the induction machine connected together through carbon brush and also copper ring. It is inserted at the tip of the rotor shaft, hence the name slip ring induction motor. Okay, and then it is also much more complicated compared to squirrel cage. So as mentioned earlier, the most commonly used is the squirrel cage. Okay, so these are some of the operation characteristics of the induction motor, or the related important terms related to induction motor. Main operation characteristic can be divided into three parts: the torque in the induction motor, the rotor slip as in induction motor, as well as the related speed. As for the torque, torque is actually rotational force. I think you are familiar with that. Rotational force in induction machine. So different torque suits different application. So it depends. Torque depends on the type of machine, either squirrel cage or slip ring, because the characteristics are different, as shown in this figure, whereby this one is for squirrel cage, while for the green one is for slip ring. Okay, as you can see, the pattern of the torque for squirrel cage increase gradually until it reached the maximum. Okay, and then for the slip ring, it reaches the maximum a bit faster compared to squirrel cage. That's the first one. That is operations characteristic. Okay, so just as mentioned earlier, different torque suits different application. So for squirrel cage, the starting torque is low, but the starting current is high. At the same time, it doesn't require high maintenance. Therefore, the maintenance cost is cheap. So that's why it is more suitable for this kind of application, fan blower, light machine. And then for slip ring, the starting torque is higher, but the starting current is lower, and maintenance cost expensive. So also it requires regular maintenance. So in terms of application, according to the torque characteristic, it is more suitable for hoist, crane, and elevator. As the crane is related torque, the application depends on the torque and also current. Okay, the second operation characteristic is rotor slip, and the third one is speed. So rotor slip and speed is actually related. Okay, that's why it's it's listed in the same slide. As you can see, okay, I'm going to highlight on the important part. So this is, in total, you have 2 speed. Okay. Rotor or motor speed, that is the speed of your rotating rotor. Okay. You also have NS, synchronized speed, or rotating magnetic field speed. This is one is for rotor speed. Rotor speed or rotating rotor speed. Okay. Okay, so synchronous speed. That is actually from here, from the on the stator part, we supply AC current on the winding. Therefore, it will produce rotating magnetic field on the stator. So the rotating magnetic field has the speed that is called as NS, synchronized speed of the rotating magnetic field. And we can calculate it using this formula, 120 F over P. F is the frequency, P is the number of pole. Pole is like north, south, okay, which will usually be given in the question. Okay, for NR, you can calculate it using this formula, NR equal to 1 minus S and S. So what is S actually? So S is slip. Slip. So it's a ratio of NS minus NR over NS. Because NS is not the same as NR. In other machine, you also have speed of rotating magnetic field, also speed of rotor, but they are the same. That one is for synchronous machine. But for induction machine, or the other name for induction machine, that is a synchronous machine, and S is not the same as NR. So NS is, so when it's not the same, so slip is actually ratio of NS minus NR over NS. Okay, slip is ratio. It has no unit. It's in decimal place or percentage. Okay. The slip in induction machine varies such that as the speed of the motor increases, the slip and torque will increase, and vice versa for decreasing speed of the induction machine. Okay, so 1, 2. Okay, this one actually comes from this formula, so I don't think you can memorize that. But for me, once you know NS and also the S, you can calculate NR. So up to you. For me, these are the 2 important formula. Okay. Okay. So just like in transformer, to produce the equivalent circuit of any electrical equipment, we are actually representing the losses in the equipment. Okay. As you can see just now in the stator, you have winding. On the rotor part, you also have winding, right? Okay. So this is stator, rotor. So on the stator circuit, we have RS, okay, to represent the resistance of this wire or winding. JXS to represent the self-inductance because the wire is wound. The construction of the wire, due to the construction of the wire, we have self-inductance XS. Okay, so that is for stator. Also, we have RC and XM. Okay, just like in transformer as well. So RC is the resistance of this core. Okay. While XMJ is the magnetizing reactance. Okay, that happens in the core as well. So this branch, we call it as magnetizing branch. Okay, stated here R1, JX1. Okay, as you can see, they are not connected because this winding is not physically connected with this winding. Okay, the rotor is just placed through the stator. They are not connected. All right. So, okay, that settle for stator. On rotor circuit represented as rotor resistance and rotor reactance. Okay, but taking into consideration the air gap power that happen between stator and rotor, our rotor resistance is always written as R over S. So this is rotor reactance, XR, but R2 usually we will present it as air gap resistance, R2 over S. Air gap resistance. Okay, so similar to transformer. So this is winding on stator, this is for rotor. Okay, on stator we also have a magnetizing branch. So they are not physically connected, similar to transformer. So when you want to combine it, we cannot simply combine it because their voltage level is not the same, etc. Okay, so therefore, you need to do some transfer, but don't worry about that. So once you combine stator and rotor, you have actual equivalent circuit. Okay. 1 minute. Okay. So at the end, this is the equivalent circuit that you are going to use, approximate equivalent circuit, whereby, okay, you have already moved this magnetizing branch from here to the front. Similar to transformer, because the current that flow through that magnetizing branch is very small, so it has no effect on the voltage drop across this. So you can simply move it to the front. Settle. So at the back, you are only left with R1, JX1. Okay, 1 for stator, 2 for rotor. So J X1, JX2, 1 minute. So when you move this to the front, you will have R1, JX1, JX2 transferred. Okay, and also R2 of S transferred. 4 components. Okay, 1, 2, 3, 4. Okay. But don't worry about the transferring part because usually you will be given with the transferred value usually. Okay. So just know that this is the approximate equivalent circuit. You have RC, XMJ, R1, JX1, JX2, R2 over S. That is the air gap resistance. If okay, it's okay. So the current, input current is I1 phase. Into the magnetizing branch is I0 phase. Here you have I2 phase. Okay. So in front here you have phase voltage. Okay, so once you have the approximate equivalent circuit, you can calculate the stator phase current or input current. So I1 phase, the other name for it is stator phase current because remember the front part is the stator, at the back is the rotor. So that's why the name is stator phase current. So I1 phase is the stator phase current. So I1 phase equal to I0 phase plus I2 phase. So I0 phase here, you use Ohm's law. Both we use Ohm's law, V over Z, V over Z. So V phase over RC parallel with XMJ, that will give you I0 phase. And then I2 phase is voltage between this and this as well, that is also V phase. over R1 plus Gx1 plus Gx2 plus R2 of S. So at the end, you will get I0 phase, I2 phase, and last one, I1 phase. Okay, 1 minute. Okay, I've explained this in the previous slide. Okay, before that, the speed. Sorry, where is the speed part? Okay, the speed. Okay, this formula and the unit. The unit is in revolution per minute. Revolution per minute. So that is the unit for the speed. Sometimes the question asks for angular speed. Okay, so angular speed omega is in radian per second. To convert it, you have to times 2 pi over 60. So I'll stop for now. We'll continue in the next video.